Hello and welcome to my channel, Finn Does Chemistry. I'm Finn and can we pretend like airplanes in the night sky are exceeding the local saturation water vapor pressure, resulting in the formation of contrails? By the end of this video, that joke will make sense. Have you ever looked up at the sky, seen a cloud formation that looks something like this, and wondered, how does that happen? These striations are called gravity waves, and no, I'm not talking about the cosmological? I'm not talking about the cosmological phenomenon, I'm talking about fluid dynamics. To understand how these gravity waves form, we need to have a look at some physical chemistry and meteorology, starting with a deep dive into the first law of thermodynamics. Let's think about the atmosphere for a second. Because of gravity, the majority of the mass in the atmosphere is pulled down towards the surface of the Earth, resulting in a pressure gradient from high pressure at surface level that gets lower and lower the higher in altitude you go. In the troposphere, that is the layer of the atmosphere closest to the Earth's surface, there's a similar temperature gradient, where temperature decreases with altitude. You can think about it as the sun warming up the Earth and then the Earth's surface heating up the air closest to it. So the higher in the troposphere you go, the lower the pressure and the lower the temperature. Now let's think about a parcel of air at ground level. Just like a little isolated cube full of air. I started doing the box just then. And for simplicity's sake, let's think of this air parcel as isolated from all of its surroundings. So there is no mass or heat transfer between this parcel and the surroundings, or vice versa. In chemistry, we call this an adiabatic system. When this parcel at ground level gets heated by the ground, it starts rising. You will, I'm sure, have heard that warm air rises, but have you ever stopped to think about why? You might say, well Finn, it's because as the parcel of air heats up, it expands, which makes it less dense than its surroundings, and because it's less dense, it rises to the top. And this is true, yes, but it's important to understand that the actual driving force for this rising is gravity. The more dense, cooler surroundings are pulled down by gravity and undercut the less dense parcel of air, which results in a sort of convective process. So there's our air parcel, and it is rising, and as it rises, it expands due to the decreasing atmospheric pressure. This expansion is actually what causes the temperature gradient, where we decrease in temperature the higher up in altitude we go, and that is because of the first law of thermodynamics. The equation we're interested in is du equals dq plus dw. That is the difference in internal energy of the air parcel is equal to the difference in heat plus the work done on the parcel. You may have seen this equation with plus or minus w, and that just depends on what direction you define the work as being done in. If work is done on the parcel, aka the surroundings are pushing on the parcel and compressing it, then the dw term is positive. But if, like in our case, it's the air parcel doing work on its surroundings by expanding and pushing on those surroundings, then the w term is negative. Now, we've already defined our air parcel as being adiabatic, which means that dq equals 0 in this system. We're not getting any heat transfer from the surroundings into the air parcel or vice versa, which means that the change in internal energy of the parcel depends solely on the work being done. Something that's important to note here is that temperature and heat are not the same thing. Our change in heat being 0 does not mean our change in temperature is 0. Temperature is actually a measurement proxy for internal energy, which is a bit confusing, I know, because we learn that something is heated, it becomes hot. The temperature increases because it's hot, and hot is heat. But yeah, it's important to understand that not only heat can have an effect on temperature, work can also have an effect. Therefore, rising, expanding air parcel, it's expanding, therefore doing work outwards. The W term in the equation is negative, so we see a negative change in internal energy, therefore a temperature decrease. In our atmosphere, we can approximate the rate of temperature decrease as being about 10 Kelvin or 10 degrees Celsius per kilometre. So say it's 20 degrees Celsius at ground level, 1 kilometre up it will be about 10 degrees Celsius. And this rate of temperature change is called the dry adiabatic lapse rate. Adiabatic because we've defined the change in heat as being 0, and dry because we are not yet considering the impact of water vapour in our parcel, because water does strange things. More on that later. So our air parcel is rising and rising, but when does it stop? That depends on the surroundings. If the surrounding atmosphere is always cooler than the air parcel, this might be because the environmental lapse rate is higher than the lapse rate for our air parcel, and there'll always be a driving force for the air parcel to continue rising. We call this an unstable atmosphere, which you can often recognise when you see these very vertically developed clouds, these cumuliform clouds, which are formed because that air always keeps rising. On the other hand, if the surroundings are always warmer than the air parcel, which might be caused by the environmental lapse rate being lower than that of the air parcel, then you've already got a stable situation where the cooler air is sitting beneath the warmer air. There is no driving force there for it to rise. We call this a stable atmosphere, and you'll recognise it when you see these sheet-like, fairly flat clouds forming, these stratiform clouds. So now we've got this model of the atmosphere where air is rising and falling, but how do the clouds actually form from this? This is where the water vapour comes into the equation. Let me introduce you to the concept of saturation vapour pressure. That is the maximum amount of water vapour that a parcel of air can hold without the water vapour condensing out. And saturation water vapour pressure increases with temperature. So warmer air can hold more water in vapour form. Now, our rising cooling air parcel has a fixed amount of water vapour in it right from the surface, and typically at ground level this air parcel will be unsaturated, which means that the air can still hold more water vapour before it condenses out. But as our air parcel rises, the temperature drops, and as the temperature drops, the saturation water vapour pressure of the parcel decreases. The air parcel will reach an altitude where it becomes saturated. The air already contains the maximum amount of water vapour it can possibly hold, and if you add any more water or decrease the temperature anymore, the water vapour will start condensing out as liquid droplets. And that is the cloud forming. Air parcel rises until it reaches the point where it's saturated, and as it then continues to rise, it exceeds its saturation water vapour pressure and condenses clouds. So far, we've only been talking about an air parcel that moves up and down. That's it. But of course, that is not what's actually happening in the real atmosphere. Air can move not only up and down, but horizontally. For example, wind. I don't have to explain wind to you, you know what wind is. So now let's imagine our air parcel being blown by the wind horizontally over a mountain range. The air obviously cannot just go through the mountain, so it's forced up and over. And as it goes up and over, it is expanding and cooling in the process. Now, if the atmosphere is unstable, which remember means that our air parcel is always warmer than its surroundings, it'll just continue off on that trajectory. However, if the atmosphere is stable, where our air parcel is cooler than its surroundings, after being displaced, it will want to return to its equilibrium position. It wants to return to that atmospheric stability. So after being blown over the mountain, it will try and return to the altitude that it was at before. Now that's all well and good, our air parcel descends back to the altitude that it wants to be at, But it does not just stop at that altitude. The air parcel has mass, which means it also has momentum. It can't just suddenly stop when it reaches its desired altitude. It will overshoot that equilibrium position. So now the air parcel is once again warmer than its surroundings, and it will start to rise back up again to that altitude that it wants to stay at. There's this buoyancy effect by the rest of the atmosphere underneath our parcel of interest. So once again, our air parcel tries to return to equilibrium, but once again overshoots that position. And you can see how this pattern can just continue on. So how does that cause gravity waves to actually form? Remember, this whole time that our air parcel is oscillating up and down, it is also expanding and cooling on the way up, and compressing and warming on the way down. So we are consistently oscillating between the air parcel being cooler at the peak of the wave and warmer at the trough. So if our air parcel at the trough of the wave has a water vapor content such that it's on the borderline of becoming saturated, when it travels back up and cools again, the saturation water vapor pressure decreases to the point where at the top of the wave, this saturation water vapor pressure is exceeded and clouds form. This is what causes that striated pattern of the gravity waves. We see this pretty commonly in the UK east of the Pennines, because when we get those westerly winds, this is what happens in our atmosphere. And you can do all sorts of fun measurements on these gravity waves. You can find the... God, I'm gonna butcher this name. The Brunt-Väisälä? You can find the Brunt-Väisälä frequency, aka how many times does that wave oscillate peak to peak per second, and relate it to the wind speed or the distance between each of the lines. So if you want to know more, those are things that you can look into in your own time. But now you know how gravity waves form. Oh yeah, I forgot to explain the joke I made at the beginning. So when you've got an airplane flying and burning a hydrocarbon fuel, it produces carbon dioxide and water. And because water is one of the combustion products, this airplane is just spitting out more and more water vapor into the surrounding air, to the point that locally, just in that area where the plane has just passed, the saturation water vapor pressure can be exceeded, and you get the condensation of clouds just along that trail where the plane has travelled. So yeah, now you know. If you enjoyed this video, I do more chemistry content like this, so check out my channel and subscribe so you don't miss the next one. Thank you so much for watching, bye!